section 4.4, which is about the area between two curves. So this is just expanding on the area interpretation of the integral that we saw in the previous section. So we know that the integral of a function is in some sense just the area underneath that function. So let's say that we want to find the area between two functions, so this green shaded area. What this says is that if f and g are continuous and f dominates g on the given interval, so in other words, if f is the larger function, then the area between f and g on the interval from a to b is given by integrating from a to b f minus g. So you take the larger function minus the smaller function. And intuitively, the reason that this is giving us that area is because we know by linearity of the integral that this is the integral of f minus the integral of g. In other words, we can just integrate term by term. But the integral of f is the area under f. So that would be this entire thing, the area under f. And if I take that, the area under f, and I subtract this, which is the area under g, then what I'm left with, if I take away this area under g, is just that green shaded portion. So that's intuitively what's happening. So we're just taking the area under f and then taking away the area under g. That just leaves us with the area in the middle. So let's look at example 1 here. It says we want to find the area bounded by the graphs of these equations on the given interval. So first, whenever we want to know what to integrate, we need to decide which of these functions is the big one and which one is the small one, because we need to be integrating the larger function minus the smaller function. So whichever function is on top, that's what's going to go here, and then whichever function is smaller is going to go here. So we need to take the integral of the large function minus the integral of the small function. So let's graph these first. So graphing y equals 0 is relatively easy because that's just the x-axis. So this is y equals 0. We can also graph the other one. So y is equal to negative x plus 10. That would be a line whose y-intercept is at 10. So it will go through this point. And then if you need to know the graph of a line, then all that you need to know is 2 points that live on that line. So you can just plug in an arbitrary x value to figure out what the corresponding y value is. For example, we could plug in x equals 4. If I plugged in x equals 4 into that line, then I would get that y is negative 4 plus 10, which is 6. So 4 comma 6 is another point that lives on that graph. And that means that the graph of that line looks something like this. Okay, so we want the area between these two curves. Now notice that these two curves do intersect over here, but that's not going to be super relevant because we want the area just above the region from negative 2 to 2 on the x-axis. So that would be just between x equals negative 2 here and this line, which would be x equals positive 2. So we want the area bounded by these four curves. And what we get is this middle area. So we're looking for the area of that trapezoid. And we could compute that area just geometrically if we wanted to. But instead, let's use the integrals to do this. And remember that to compute an area like this, what we need to do is we need to take the integral from this x bound to this x bound. So this will be the integral from negative 2 to 2. And then we need to take the top function minus the bottom function. So just from the graph, it's clear that the more complicated linear function is the top one, and then y equals 0 is the bottom one. So the top one is going to be the negative x plus 10, and the bottom one will be y equals 0. So we'll take the top function, which is this, and then we'll subtract the bottom function, which in this case is just 0. So the area is going to be given by this integral. That'll be the integral from negative 2 to 2 of, if we simplify the integrand, it's just a negative x plus 10 dx. And now I can integrate this term by term. So this will be the integral of negative x turns into a negative x squared over 2 because I increase the power by 1 and then divide by the new power. I do the same thing to the 10, so the antiderivative of 10 will be a 10x. And then I'm evaluating this, now that I've taken the antiderivative, I'm evaluating from negative 2 to 2. So that means I should plug in a positive 2 and then subtract what we get whenever we plug in the negative 2. So this will be a negative 2 squared over 2 plus 10 times 2. That's the evaluation of the antiderivative at positive 2. And then we need to subtract the evaluation at negative 2. So that would be minus a negative 2 squared over 2 plus 10 times the negative 2, because we're plugging in negative 2 into our antiderivative for the second part. So now we can simplify this a little bit. So this first thing is a negative 4 halves, so that would be a negative 2 plus a 20. And similarly for this second set of parentheses, what we'll have is a negative 4 halves again, so that will again be a negative 2, but this time it'll have a minus 20 as its second term. And this is 18 plus 22, which is 40. So that means that the area of that trapezoid, if you were to compute it just geometrically, would be 40. In other words, 40 square units. Okay, and that's the basic idea behind this section. We'll see some slight complications in the next couple of examples, but that's essentially it.